Hi guys, today I'm going to use a simple example to illustrate how game theory can be applied to a stochastic model for decision making. Before the topic of game is introduced, we usually view the problem from the optimization perspective. But we'll realize that you are not the only individual in the situation, and your profit is affected not only by your decision, but also by the others' decisions as well. Also, the other's decision is affected by your decision. Then, you and the others will reach at an agreement, where no one has an incentive to deviate. We call this as a Nash equilibrium. Now, let's look at the example. There are two servers, server 1 and server 2. Their job is to transmit the message. When the message is successfully transmitted, each server gets a reward of $1. But the two servers are not perfect, so there is a probability that the message is lost. If it is lost, servers got nothing. Also, each server can transmit the message only when it is active. And it's not free to be active. You need to pay a cost of C. Each server can choose to be active or inactive. If both servers choose to be inactive, that means they don't want to do the job. Of course, they don't pay anything, and they got zero reward. So the payoff is zero for both of them. If one of the server chooses to be active and the other chooses to be inactive, then the message is transmitted by the active server, and the active server needs to pay C. Note here that as long as the message is successfully transmitted, each server can get the reward. So even if a server chooses to be inactive, but the active server transmits the message successfully, he can also get the reward. If both servers choose to be active, then the message will be transmitted by the server with a higher successful rate. But both of them need to pay C. Now let's look at the case that P1 is greater than C, P2 is greater than P1. If you are server 1, you actually have the intention to be active, because if you're active, your expected payoff will be at least P1 minus C, which is greater than 0. It seems like it's better than you did nothing. But you look at server 2, you're thinking, he's better than me. Why not let him do the work and I just take the free ride? At the same time, server 2 might think the same. Although server 1 is not as good as me, but he's not that bad. Let him take the job and I will just relax. Now let's look at specific example where C equals to 0.3, P1 and P2 equals to 0.6 and 0.8 respectively. If server 2 chooses to be inactive, while server 1 is active and takes the job, it means server 2's expected payoff is 1 multiplied 0.6. But if server 2 chooses to be active, then his expected payoff will be 1 multiplied 0.8 minus 0.3, which is his operation cost, that equals to 0.5. 0.6 is greater than 0.5. That means even if server 2 is better, he will be better off if he takes the free ride of server 1. But what if P1 is 0.4? In this case, if server 2 chooses to be active, his expected payoff is still 0.5. But if he chooses to be inactive and takes the free ride of server 1, then his payoff is 1 multiplied 0.4, which is less than 0.5. This means if server 1 is much worse than server 2 cannot count on him, and he should do the work himself. It also reveals another interesting phenomenon in reality. Playing the game is only interesting when you and your opponent are of similar level. Let's draw the Nash equilibrium in this plot. it can be seen that if your successful transmission rate is less than C, it's better to remain inactive. If one server is much better than the other server, and this better server's successful transmission probability is greater than C, then he should stay active and the other server will choose inactive. The interesting region is actually the upper right corner, where the servers don't differ that much. In this region, if one server chooses to be active, the other server will choose to be inactive. If one server chooses to be inactive, the other server will choose to be active. Now, let's imagine that you are the boss of these two servers. And what you care is not the individual profit, but the sum of that. So what will you do? First, you expect only one server will be active each time, because even if they are both active, the work will only be done by the better server. Also, you expected the better server to be active, because if he's active, the expected payoff will be better. But you can't force them to do so. What you can do is changing the game rules. You can make the game fairer. For example, you can set a rule saying that if a server chooses to be active and the other chooses to be inactive, then the inactive server needs to pay the active server a certain amount of money. This actually relates to another topic that's called mechanism design. We will introduce more details in the following videos. If you like this example and want to know more details about it, you can come to my personal webpage or use the following link to access the complete paper. My name is Jason Wang. I'm a postdoc researcher in the math department in the University of Amsterdam. Before that, I obtained my PhD degree in the University of Melbourne, Australia.